The broadcast is now starting. All attendees are in listen-only mode.
All right. Good morning, good afternoon, good evening, good night, wherever you are in different parts of the world. I hope you're all happy and safe and doing good in this environment that we have globally. We are so excited today to have this IFEES GEDC IUC webinar, global webinar for improving the quality of engineering education and using technology to do that. One of our key sponsors, Siemens, is helping make this presentation possible today, and we have with us Gil Morris, who is the academic programs, the project manager for the academic programs at Siemens. So over to you, Gil.
Thank you, Krishna, and thank you to all the participants for attending today's webinar. Siemens Digital Industries Software is committed to education and workforce development. Now, certainly the current pandemic has put a new twist in our daily lives, but we're committed more than ever to help educating the next generation of engineers by providing access to our software, our learning resources, and perhaps even more importantly, the knowledge of our of many industries through our subject matter experts. So with that said, digitalization is changing everything around us, and our workforce needs to be prepared for the jobs of the future. And given the aging demographics of the current workforce, myself included, there's a lot of pressure to fill the talent pipeline that's going to be needed in the future. At Siemens and at our customers, we talk about Industry 4.0, IoT, and those sort of things. And we use terms like digital twin and digital thread when we describe product development cycles, manufacturability, and in-use scenarios. Additive manufacturing is definitely revolutionizing the way we make everything, and it's certainly enabling greater innovation in product development. So today you're going to hear presentations from the University of Cincinnati, where I've had the privilege of working with the faculty and students to implement several of our digital tools across the curriculum. So in a sense, UC is implementing what I would consider a digital thread in their engineering program, enabling their students to really understand the connectivity between the fundamental physics that they're learning and trying to apply. UC has also done extensive research in additive manufacturing. As I said before, it's revolutionizing the way we make everything. And they were doing this even before it became a really hot topic. So you're going to hear a presentation on this as well, on this new exciting technology and how this team is executing their plan to bring additive manufacturing into the classroom. So with that said, I'd like to introduce our guest speakers. Dr. Jay Kim, professor in the Mechanical Engineering Department and Materials Engineering at UC, and he's currently serving as the department head. And Dr. Sam Anand, professor of mechanical engineering and director of Center for Global Design and Manufacturing at the University of Cincinnati. So with that said, take it away, Sam.
Thank you, Gil. Thank you, Krishna. I appreciate those comments here. As Gil mentioned, my name is Sam Anand. I'm a professor at the University of Cincinnati, and I serve as the director of the center. So what I'm going to show today, along with Dr. Kim, is our immersion into using Siemens software in the curriculum in a seamless way for exactly what Gil talked about, maintaining the digital thread, the digital twin, and ensuring a seamless integration of Siemens software into a curriculum so that students understand the power of simulation. So the Siemens Simulation Technology Center was formed in 2017, and it due to a giant effort from Siemens, and that is the basis of what started this whole thing here. So moving on here, so just wanted to give you an idea of what the center goals are. Of course, I serve as the center director. Professor Kim serves as the education director. The idea was to revolutionize engineering education and research, particularly as it applies to industry-specific research. So the idea is to introduce simulation across engineering curriculum from early courses, so the student learn the power of simulation, and they understand how simulation can help in predicting and modeling rather than doing everything practically, so it's much faster, easier, and a time compression. And we also want to bring in industry-specific research and industry-specific problems back to the classroom in conjunction with using the simulation methods here. And finally, we want to develop a set of simulation apps in the basically multi-domain simulation apps that can be industry-specific, but can be brought back to the classroom so that students get a real-world experience of what they are learning and how it is used in the industry rather than going through a fictitious example. With that said, moving on here. So let me give you a quick profile about me. I've been in the University of Cincinnati for 30 years. I got my master's and PhD at Penn State University. My primary areas of research are in additive manufacturing, modeling, and subtractive manufacturing modeling. We also do a lot of work on industrial Internet of Things, augmented reality, and Industry 4.0 kind of research here. So that's a quick overview about me. Moving on, let's get to the next gist of it. So this is sort of a big picture of how the course integration happens. And there's two separate compartments here. On the left side, you see the integration in the undergraduate engineering curriculum of all the Siemens tools and Siemens simulation tools that Professor Kim is going to describe in the latter part of the presentation. On the right side, you see the additive manufacturing and the IoT and the Industry 4.0, 5.0 tools that we are in the process of integrating. So I'm going to talk about what's on the right side, more about the additive manufacturing and the digital manufacturing part. And then in the latter part of the presentation, Professor Kim is going to describe the integration into the undergraduate curriculum. So quick outline here. So we'll talk about the Siemens Center website and how we integrated Siemens NX tools into our geometric modeling apps that we use in our course, and then into additive manufacturing tools and apps that we use in our two sequence courses here. And then we'll talk about other tools that we developed in additive manufacturing compensation, lattice structures, and so on. I will describe specifically industry outreach and how these tools bridge what happens in the industry and how we are relating what happens in the industry to bring it back to the classroom. Once in the latter part of my presentation, I will talk about the IoT and the digital twin integration in design and manufacturing with two examples of actual industry examples that we bring back to the classroom. So that is the agenda for my part of the presentation. On the right side, you see the set of menus and tools and examples of what we've integrated. That's what I'm going to go through. So basically, if you look at it, on the right side, you see the courses, manufacturing courses we have integrated. We have an undergraduate course of manufacturing process, a dual level course, which is a senior and a graduate level course on CAD for manufacturing and competition methods in additive manufacturing 1 and 2. And eventually a dual level course in Industry 4.0 digital manufacturing. Now, some of these courses are completed, and some of these courses are in the planning mode. The kind of tools we used on the Siemens tool set, you see on the right hand side, we use NX, NXCAM, NXCAD, MindSphere, Sematech. And then we also look at how we bring together some of these tools into the apps where it relates to industry. So I'm going to define and describe some industry collaborations that you see on the bottom right-hand corner. So those would be the examples that we take away, that we bring back to the classroom. At the bottom of the window, you see an example of all the tools integrated into NX, some of our tools here, and I will show you some of these menus as we move along here. So first thing is we have a Siemens Center website. Obviously, all our tools, all our apps are sitting in this website, and with case studies, examples of classroom integration that's replicable, and information on how to download this and install it and so on. All this is available at the UC Siemens Center website. It has a link to Learning Advantage from Siemens, so you can use either the UC website, the university website, or the Siemens website to download some of these tools here if you wanted to. So how do we go about doing it? Just a quick overview of the AM toolbox here. So we integrate the NX API methods with using C++, Python, open source software, or with OpenCV. We integrate with computational geometry algorithms. And what you see are the menus that you would normally see on the Siemens NX. You would see some of our menus. So you can use it for the additive manufacturing apps here. So all this is, we write these apps, and basically they are DLL files that you drop in so that you can see these menus populated on the NX software itself. So examples of geometric modeling apps here, you can see we can take this is taught in the CAD for manufacturing course, where we teach computational geometry, geometric modeling, curves and surfaces. So students would be given these assignments where they develop the algorithms and do the homework, but they can come back and verify it using the apps we develop. So it gives them a reinforcement of what they learned by doing the homework and coming back on each of these things as part of the class. And these are fundamental transformation methods here that we teach. So how one would go about doing it. All this is integrated into NX so they can seamlessly view it. Similarly, we teach a whole lot of information on curves and surfaces. So we teach everything from Bezier curves to B-spline curves in the first course. So the students have an opportunity to take the homework, work on it on their own programming language, MATLAB or Python, but they can come back and verify these methods using the apps that we develop here. All these apps are available within NX, that they can verify their homework. Example of surfaces, we teach once again, different types of Bezier, B-spline surfaces, and so on. So these are our own specific apps that are integrated with GUIs and so on, that students can come and use it and verify it and play around, not only to verify their homework, but understand the concepts much better here. The idea of simulation is to give the students an ability to play around. And so they look at what if scenarios, what if I change this, what happens to it? That is crucial for them to understand and master the learning process here. So moving on, those were the geometric modeling apps that's introduced in the first course. In the second course, the additive manufacturing one, there's a whole bunch of additive manufacturing apps, including support tools, DFAM tools that you see here, support generation tools, build parameter tools, and so on. And then our own producibility index that tells you build orientation optimization. So all these are apps that are developed internally by us, and they work on any kind of a part. You can take an STL file, or you can take a neutral file, push into NX, and then work on it from Siemens NX. So these apps are integrated into Siemens NX. So more examples of these are examples that you would see. These are the apps that are integrated, and basically you can see these apps. As you can see, some of them are, that's what you would actually see, the apps as you work and as you see all those things. So the bunch of apps that you hear about support structures, these are DFAM apps. All of them are integrated. There's an example of a DFAM app that's working. So you can see how basically it goes through the process, does a layer by layer analysis, and then detects all the features. So this is already integrated into NX, and so that is what you would see. So you can see the color-coded DFAM features that are highlighted here. So that input is given. So we have more apps on calculation of centering area, cusp height, build time. All these are integrated. You can calculate the actual build time, cusp error. All this is working on the NURBS geometry or the CAD geometry of the part itself. So we're not working on STL files. So all this is brought together into one final metric, what I'm going to call as a producibility index, that gives us an idea of how to do build orientation optimization, so that you can take all this and find out the best build orientation for the part, particularly in metal additive manufacturing. So here's an example of the flow that will happen. So you take the part, you develop the CAD and develop the supports there. And once you develop the supports, you look at DFAM parameters, you do the support accessibility for removal of supports, and finally, the orientation optimization. So this is how it's going to look like, the producibility index here. basically goes through and looks at developing the part, the orientation, and then the build parameters. So finally you can look at the producibility index by doing an orientation optimization here. So those are the set of tools, and we have developed a whole bunch of tools for design optimization, including topology optimization, looking at lightweighting parts, looking multi-material parts, and so on. So a whole bunch of other tools, including thermal compensation, build orientation for thermal compensation, topology optimization for AM parts, specific to additive manufacturing, lattice structures, and multi-material lattice structures, and so on. So we teach this in the second course of additive manufacturing. So that is our objective. So here is a repertoire of what you would see in these apps here. Some of these are topology optimization, specific to additive manufacturing with DFAM constraints. These are examples of lattice structures with multi-material lattice structures or stochastic lattice structures. So this is an example of how we predict thermal deformation and do thermal compensation on the NURB surface itself. We teach all these things based on the work we've done and on the industry contracts we work on here. So to bring this all together, so this is sort of where does it all connect to the industry? So these are examples of 4 industry contracts. So this is a DMDII, which is a UI Labs federal government contract that we worked with GE Global Research on. It's a project, the 18-month project on developing a virtual certification of the metal powder additive manufacturing process. We worked with GE and University of Cincinnati, Urbana-Champaign, and a couple other partners here. So this is an example of work we did with GE Power and Water of using some of the apps that I talked about here and using an orientation optimization. So this is sponsored by Honeywell. There's a research contract where we're using compensation based on using neural network here. And this is a contract from GE Aviation on using DFAM analysis. So we are bringing together some of the apps that we develop into the industry, using it for industry and bringing that learning back to the classroom. That's the whole idea here. So the second part, I got a few things to talk about. Since Gil talked about digital twin and digital thread, we do a lot of work on IoT and AR, VR integration into the classroom, and we're developing a separate course on Industry 4.0, 5.0 here. So that is the course that I'm looking at here. So we are looking at a separate course in Industry 4.0 where we're going to use Siemens MindSphere, Cimatec, and Mendix for looking at IoT and AR, VR integration on the factory floor. Just to give you an example, this is a DMDIA project where we used computer vision cameras to look at older legacy machines and gauges and parts where there's no sensors, and then video record those particular machines and the console and so on. In real time, we analyze those values and then use those values using and push it through MT Connect, which is a standard, so that people can view it here. We worked with Raytheon and Furcia on this project. Just to give you an idea here, this is how it looks like here. So this is a mock panel with all those values here. These could be the gauges on a CNC console. This could be the LCD panel on an injection molding machine. So what we have is a Logitech camera that's looking at it here. It's a $200 camera. And then it's recording images at 30 frames per second, and each frame analyzing, getting the values here and pushing it into MT Connect. And this is the MT Connect output that you would see in an office far away or in a remote location. So it gives you an idea of how we can acquire data from legacy machines. So this is one of the projects we are trying to bring together into the classroom. A second project is using mixed reality, where we're using AR, VR, and mixed reality context so that you can use an iPad to look at a machine and gather sensor data on the fly here. So this is the thesis that's just completed by a student here. Let me show you one video. So this is a video of the student actually at a factory, the Volvo factory, looking at that particular machine, and he's going to use his iPad to look at this machine and bring all the sensor values in a mixed reality interface so that all those sensors, the values can be looked at right there, and we can do it for any machine. So all these green and red balls that you see are the sensors and the location of the sensors, and those are the values here, and they come up automatically, and basically it's pulling it from the cloud in real time, and that's what goes on here. So this is a project. So we're going to bring both these things into the classroom when we're done here. So as you can see, he's pulling up a particular value and correcting the value of this particular sensor here. And once he fixes it, it's going to turn green. So that is my part at this point. I'm going to hand it over to Professor Kim because he's going to take over and talk about the integration of Siemens tools in the sequence under their courses in mechanical engineering. Krishna, if you can hand over to Professor Kim.
Yes, it's handed over. Over to you.
And let me go to this slide mode. Okay. Again, thank you, everyone. This is, in fact, the education side-centric side of Siemens Center at UC. Basically, what we try is a new approach in engineering education. It's engineering education to take a full advantage of the power of modern simulation technologies. So this actually stemmed from obvious question. It's like there have been tremendous development in computing power and the software technology. Then still we were teaching fundamental courses like solid mechanics and fluid mechanics pretty much the way we used to teach it 30 years ago when I first came to UC, or even before, 40 years ago when I was a student. So I think it's a time to change this. And the idea is exposing students to simulation through multiple well-designed connected courses, starting from earlier courses like sophomore. Then in the end, then we try to develop engineers with the strong fundamental knowledge as well as the simulation capability who can do both. So in fact, even today, if you go to industry, then often you see a special group of engineers called the simulation engineers. So why do we do that? Like, so all design engineers, analysis engineers, they can, or they should be able to use simulation software, much like they are using calculator or any fundamental tools. So we wanted to make that happen. Then also along the way, motivate student learning in fundamental courses. So not just to teach simulation software, but to teach fundamental knowledge very well. Okay, then these are actually the courses that we integrated in the series. So it starts from freshman course, engineering graphics, where we teach NX graphics. So NX graphics is taught as an essential utility. And of course, the students use NX graphics to make drawings in the later courses, but also use NX graphics as a pre-process of FEM and CFD application. Then in the middle of the curriculum, then we teach NASTRAN, FEM, in solid mechanics in fourth semester. Then Amesims, which is a lumped parameter simulation software in rigid body dynamics. And STAR-CCM, a CFD software in fluid mechanics. And heat transfer, again, STAR-CCM is introduced. So these are two real fundamental courses that define mechanical engineers. So mechanical engineers are proud of having, learned these courses, and these courses define mechanical engineers, but also these courses often give the biggest trouble to mechanical engineering students because they are so hard, so difficult to understand. Then later, we use this software in design courses. By senior year, then our students are capable of using this software. Then depending on their project of choice, then they use a NASTRAN, STAR-CCM, or Amesims, or multiple of them. Then some advanced undergraduate students and graduate students take elective dual-level courses. So we have an introduction to FEM, which is a typical FEM course to beginners. Then we also developed specially It's like a simulation of a multi-physics systems. So these days, engineering problems becomes complicated. Then you have to deal with both the fluid mechanics and the solid mechanics, or thermoacoustics, all those kind of things. So then we have an acoustics course where we also teach and use NASTRAN. So that's actually what we are doing. Is introduce a simulation early on, then it's a repeated exposure, but well managed, developed, and well thought out sequence. Then typical course module is designed in such a way. So we usually give one or two very simple example problems. It's like a simply supported beam that you can easily obtain exact solution. Then students do validation in both ways, like simulation produces a correct result. Then also this is a theoretical process produces correct result in both ways. Then along the way, students learn understanding about basic fundamental concepts and the theories. Then we have a relatively simple problem, but that cannot be solved exactly. So this is the way students understand power and the utility of a simulation software, why simulation software should be used. Then finally, a project that requires more realistic engineering thought. So this is like train students how to formulate a simulation problem out of an engineering problem, because in real world, no problem is given as a simulation problem. You have to see the design problem or business problem that has to be defined and converted to simulation problem. So they learn that. Then also they learn how to interpret the results and apply the simulation results to design. Okay, so the first class is a graphics course. So we have a freshman full semester graphics course, as well as 2 crash courses like that is delivered in maybe 3-4 weeks for students who transferred. So they didn't take our freshman graphics course, or all ME students have taken freshman graphics course, but if chemical engineering students want to use NX, then they have crash courses to take. So this is one example the student built, like using solid modeling. Then they make some exploded view, then 2D drawings, then bill of materials, those kind of things. So it's typical design course, but we use NX graphics, which is the highest level, highly comprehensive design graphics course software. Then also in this course, being the first course, then we train the students so that they can self-navigate. In modern days, there are abundant of information, but you have to learn how to utilize them. Okay, so in this case, students are given with the resources like our Siemens Simulation Center at UC. We have a center website that also Dr. Anand showed you just before. Then each course module is there. Then also some YouTube-based tutorials and so on that you can use that. Then Siemens also provides learning advantage, which is a really comprehensive. Then you can learn all questions from there. Then also software itself, like NX in this case, as a documentation. Then we also have a NASTRAN documentation. So students learn the ability to navigate through all this information and self-teach. And this experience carried to all other courses, okay? So then NASTRAN is taught in undergraduate course, solid mechanics, then machine design, then undergraduate FEM, then dual graduate level, then we have another FEM course too, then also modeling and the simulation of multi-physics systems, usually industry-derived system problems, then acoustics that you will see some examples. So this is like a solid mechanics. It's like a combination of a simple problem and intermediate problem. So this is like an ASTM tensile test specimen. So one nicer thing is in the middle section here. So exact solution works very well. Exact solution is very simple to obtain. Simply force divided by cross-section area. Then students can compare the stress level. Then around this whole area, then there is a stress concentration arises. Then they learn why stress concentration occurs because of the geometric discontinuity. Then they also compare this solution to Cauchy's solution, that kind of thing. So students learn like a stress concentration, why that happens, and they should consider that in design. Then also this problem can be solved either by using 2D element or 3D element. Then pros and cons of 2 elements. Then what do you choose? Okay. Then in 2D element, if it's chosen, then you have to decide either plane stress analysis or plane strain analysis. So in this case, this is plane stress problem. So such kind of a teaching, as well as learning how to use NASTRAN. Then this problem is taught in elective senior level FEM course, then using NASTRAN, and the students solve a more realistic problem, in this case, bike structure chassis, okay? Then first they do stress analysis and deflection analysis. Then they have to decide, what kind of load cases they have to use. Then impact factor, how does it have to be reflected, or that kind of things. Then the problem is converted to FEM problem, okay? Then they can solve it. Then also further, they learn how to do design optimization using built-in function in NASTRAN. So in this case, this is a constraint optimization to minimize the weight. Okay, so of course, this is possible because this is a senior level and the students already have some experience. Then this is an example of acoustics. So basically here, this is an expansion chamber like a muffler. Then they obtain the solution and compare with the exact but 1D based solution. Then also they check structure, acoustic coupling. Does a coupling have to be considered? So learning points, biggest one is here, acoustics problem can also be solved by FEM, okay? Then structure acoustic coupling case. So that's what students learn. Then of course, not to mention design of expansion chamber, concept of natural frequencies, those kind of things. Then Amesims. Amesims we teach that in rigid biodynamics and multi-physics systems too, also to support student activities. In our case, formula essay competition. So formula essay is a student, each year they build a race car, miniature race car. So this is to support that. Then we help the students develop like a full car body model for like suspension design, then lab simulation, then also some force history in components, that kind of thing. So this is a lab simulation animation. So formula essay team, you see typically we have about 20-30 students. So with this, then they can have some virtual model and simulated lab races several times before actually going there. Okay, so then going to STAR-CCM, we teach and use STAR-CCM in undergraduate course fluid mechanics and heat transfer. Then of course some students use STAR-CCM in senior design. Then dual and graduate level course, again, multi-physics and acoustics. So this is an example. It's like a design of the heat transfer pin. So at this figure, there are 1, 2, 3, 4, 5, 6 fins. Then flow is in this direction. Then this is like a flow analysis first. Then conduction, convection, then heat transfer analysis. Then this is like heat transfer capacity or performance. Then as you can see, as you increase the number of fins, then of course, because there are more heat transfer surface area, then heat transfer rate increases. But at some point of time, too many fins start to restrict the flow. So the flow velocity becomes slow. Then the forced convection, you have a smaller heat transfer coefficient. So because of that, it provokes some design thinking to students, like some optimization. So adding more doesn't necessarily mean good thing, okay? So then, of course, then doing this, then students also learn convection, conduction, those kind of things, while applying that to realistic problem, not really simple textbook problems. And then this is a little higher level. It's a simulation of multi-physics systems showing the analysis of a fluid structure interaction. So this is a simplistic case, like air flow is going over the cylinder surface and excites this beam. So even though this is a very simple problem, students learn how to do fluid structure interaction. So then they are ready and they are capable of attacking more challenging problems like aeroacoustics problem or aero or elasticity problem, then a flutter problem in airplane wings, those kind of things later in their career. Okay, then this is another example. So this is like a simplified additive manufacturing, metal additive manufacturing. Then in additive manufacturing, because motion is involved, then also melting, then solidification associated with phase change, then conduction, convection, all those kind of things. So first step to do the design analysis is heat transfer analysis. So this is one of those cases. So it shows, how the moving conditions can be reflected, then how the heat transfer analysis can be done, then how melting and the resolidification can be simulated, even though this is highly simplified. So that's actually what we have been doing. So then, in a sense, in reflection, I would like to summarize what we have done and some possible potential next steps. It's like we have been trying to modernize engineering education. So I believe we can do much better job doing this way. It has been 3 years since we started this new approach. Then students like it, then also faculty love it because so certainly not all faculty are equipped to teach simulation and simulation technologies in their courses, but they can get the help. And then we also provide course modules. Then not to mention students, then especially UC is a co-op school. So students learn this software, simulation technologies, then they actually apply that in their industry co-op assignment. Then they get a good reputation, some praise because they are capable. What some of their engineers in the industry cannot do, then our engineers can do that. Okay. So then, of course, students learn better in my mind. However, we can do better. Okay. First of all, because of the limited time, we have been doing this about 3 years, and including probably preparation time, maybe about 4 years. So far, this has been done only to mechanical engineering. So obviously, the same approach can be or should be expanded to other programs in our school first. So I think expanding this to aerospace engineering is the simplest because to some extent, aerospace is a sort of a special set of mechanical engineering. So it's easiest to extend. So almost exactly the same way we developed then can be applied to aerospace curriculum and courses. And chemical engineering, they use a lot of CFD and heat transfer analysis. Chemical, civil, then biomed. Then of course other schools. So any other schools in the audience, or if you know, then we will be happy to help them to implement this in their curriculum, then share the course modules we developed and some other experience and know-how. We will be happy to do that. Then even though this is highly effective already, I think we can make a further improvement. So one thing I want to do is developing 1 or 2 projects to be carried through multiple courses throughout. So for example, in freshman graphics, students develop solid model and all the drawings. Then in manufacturing course in sophomore or junior year, then they print it by using 3D printing. Then in solid mechanics, they can do like a stress analysis and fatigue analysis of that what they printed and designed. Then they bring it to heat transfer course, then see how the heat transfer is it's performed in that kind of a part or system. Then all the way to senior lab, then they can do the thermal testing, or if it is a mechanical components, then maybe stress tests or vibration tests. So using one or two, then carried all the way through, then it is going to be really good experience for students that truly integrate these courses in a very meaningful way. Then, of course, anytime projects have a more substantial design implication, then students are more excited to learn. So we keep try to improvement course modules and the example problems. Then hopefully we can do this, but if we can find good partners, then implement this with the multiple partner schools. Yeah, these days you can do WebEx meetings or GoToMeetings virtually. Then a lot of courses are offered from online anyway. Then certain project can be done with across maybe 3-4 different universities, even different countries. And students can in fact obtain more multidisciplinary collaboration across different languages even. So that's what we plan to do. Okay, so that's the end of my presentation. And let me actually end here. Then I think it is going to be followed by discussions.
Fantastic. This is just amazing presentation, Dr. Kim. A classic example and a fantastic example of how industry and academia are collaborating in this day of technology in all dimensions. And I really appreciate your offer to other institutions to join you in this adventure and this new direction. I'm going to give first an opportunity for the team to have maybe add things to the presentations. Both Sam and Jay, and now we have Dora Smith who's the head of the academic programs at Siemens. She had just sent us a text message with a link to some other examples of this kind of thing. Perhaps she might have some comments, and then Gil Morris might have some comments. So let's just first have the team of 2 from University of Cincinnati and 2 from Siemens just make a few comments before we open it up to the questions and comments from the audience. We have over 300 people here, and several questions already have been posted. So Dora, would you like to make some comments, please?
Sure. Krishna, can you hear me okay?
Yeah.
Great. Well, first of all, I just want to thank Jay and Sam and Sam for their hard work. Hopefully you guys can all see that they're doing so much to really, close the skills gaps that we've talked about and really improve the skills of future engineers in some very key demand areas like simulation and additive manufacturing. I also want to thank Gil on our team because he's been so close to this project for the last 3 years. It's been a great collaboration. And our goal here is to work strategically with great partners and schools like the University of Cincinnati, but then scale those best practices, those lessons learned, that curriculum and content internationally. And so, Krishna, you're giving us a great opportunity today to share these resources, and really look forward to getting the feedback from everyone, how they're able to integrate them in their own places. Thanks.
Great. The link that Dora Smith had sent, we have broadcasted to all the audience, so you should be having it in your site there. Gail, would you like to add, and maybe Sam, add to this before we move on to the questions of the audience? Go ahead, Gail.
Sure. Yeah. Yeah. It's been an honor to work with the UC folks, and I've certainly learned a lot myself. But one of the observations I've witnessed is just seeing the inter-department communication. And again, this is I think being reflected in industry, where no longer can we work in does industry work in silos, right? And so just to see the collaboration amongst the professors within the ME department, and then I'll say through osmosis, it's trickling into the aerospace, and so it's been refreshing to see how this has facilitated more communication, better communication and collaboration just within the UC faculty. So yeah, very, very impressed with that.
Great. Sam, jump in.
Yeah, thank you, Krishna. And I do want to reiterate and concur what is said both by Dora, Gil, and Jay. I think it's an immersion into simulation throughout the curriculum. And also into the graduate level. And idea is to bring back not only simulation to the classroom, but also help students understand what real world industry problems are And these tools are being used day in and day out to solve simulation problems in the industry. So that is where the rubber meets the road, where students understand the value of these kinds of tools. So it's not just going through the motions, but understanding this is what they would be doing if they go work in the industry, and that is crucial to bring back to the classroom.
Great, thanks, Sam. Darius Ferdinelli, you had an interesting comment, question. I'll actually unmute you. Can you speak for yourself?
Yes, first of all, can you hear me fine?
Yeah.
Good. First of all, I'd like to applaud the effort done there. This is outstanding and a great example of what can be done when parties put together their minds to make this happen for the benefit of the students. So I applaud the effort here. I've seen this at other universities where they struggle with trying to get this systematic approach together. What challenges did you have to make this happen, and how long did it take to get everybody to agree to put this very systematic approach to learning simulation in your curriculum?
Okay, this is Jason.
Can you give us the affiliation also? Where are you? Which
Yes,
are you?
I'm with Altair Engineering, based in Troy, Michigan, and I work on our university outreach program, trying to help universities with using of CAE technology also in curriculum.
Yeah, response to him. Anybody
Okay,
from?
this is Jay Kim, and let me actually answer that and give my kind of thought about that. Okay. In fact, this kind of approach I have been thinking for a long time. Then it was made easier because generous support and gift from Siemens Technology Simulation Division. And it is to some extent, there is some inherent mismatch in academia, because if you look at how long it takes a university faculty is developed, you are talking about 10 years, maybe BS, MS, PhD, then maybe some period in between. Then faculty are working both education and research, and there's a tenure system, emphasis in research, and so on. So it's like some inherent time lag and mismatch. Then the need and the obvious things are not really reflected immediately in engineering education. And because of that, in fact, I had some difficulty to implement this concept, basically how to mobilize faculty members. And for example, certain faculty have been teaching solid mechanics the way he did for the last 10 years. Then why do you expect him to change by learning how to effectively use NASTRAN in his course and so on? So then my approach was then, if we have some team, then we build the course module and initially take over that part, like simulation part of his lecture or her lecture. So then to do that, that was possible to do this. But again, we were, very fortunate to have Siemens support. So I think the best way is, or most effective way is with this kind of concept, then you can do some fundraise. Not a lot of money is necessary, but hiring some graduate assistants to develop course modules and to implement that. Okay.
Great, thanks, Jay. Anybody else wants to comment on that, Sam?
Yeah, if I may, I think I want to concur with Jay. I think the key is to impress on the faculty that this is going to make their actual imparting of the instruction much more effective and enjoyable for the students, and also relate to the fact that eventually it is going to be easier for them to teach the concepts because it is conjoined with the simulation and students see the benefit of it right away. So the effective retention of those concepts in the classroom is much better when we do this. And once the faculty realizes that particular aspect of it, then it starts to be easy. Obviously, there needs to be some support during the initial phases of getting the software and all those things integrated into the class in the form of TAs and so on. But the convincing has to happen where the faculty realize that this is going to benefit them and the students, and then it's an enjoyable experience. That's when it happens.
Okay, here's a question from the audience related to the student engagement and the characteristics of the students and how to motivate the students to get maximum benefit from this type of sim-based learning.
Yeah, to me, it is like seeing how they can solve a realistic engineering problem. Looking back my student years, the biggest frustration I used to have is in solid mechanics or fluid mechanics, you learn so damn difficult theory, then end up solving very simple ideal problem. So, what am I going to do when I go to real industry and have to design some realistic things? So that question can be immediately answered. So that it becomes the biggest benefit of this approach.
So just to add to what says, I think relating industry and real world situations, not only the real world industry problems, but also bringing industry people into the classroom, which we do very often, to emphasize to the students that what they're solving is not a fictitious problem. This is what engineers in the industry do day in and day out. That's how they actually solve problems. That makes it easier for the students to actually embrace this whole idea and understand that this is not some going through the motion, but it's going to help them as soon as they get employed in the industry.
Great. That was that question was from Felix Arokia Raj. So thanks, Felix. Kanku Lubale asks about chemical engineering. Can some of these softwares be used for simulating chemical stuff like dissolution in a solution and so on? Any thoughts on that?
Yes, we are actually trying to apply this to chemical engineering. STAR-CCM Plus is a CFD software that you can solve a fluid flow, heat transfer, and so we are planning to.
Okay. What's the software? Tell a little bit about the software and the licensing and those kinds of things. Anybody want to comment on that?
You mean chemical engineering application?
No, in general, yeah. I think the simulation software and
yeah, this can be done with, of course, other softwares too, but because we have a Siemens supports and a generous software gift as well as a financial gift. So our system is based on Siemens software. NX Graphics is a graphics software. Then NX NASTRAN, which is FEM. Then STAR-CCM Plus, that is a CFD. Then Amesims is like a lumped parameter multi-physics simulation software. That's what we are using.
the open source licensed, I guess that's probably.
No, so Gil can answer that question.
Yeah. So we offer multiple flavors of our software. We have free student versions that any student can go download. We've also got what we would consider the commercial or that we bundle up in academic bundles. So, and again, the whole intent is for these software packages to be used in the classroom or for research purposes that can be published to the general public. And again, you can contact us. We've got a grant application process that we're happy to walk our academic partners through and help you get set up with all the resources that we've got. So yeah, we can provide whatever licenses you need and whenever you need them.
Great, thanks. Okay, let's see. Somebody wants to speak to Dr. Okay, let's see. Okay, there's a question from Juan Nicolaitis is IUC, I think, has a co-op program, right, for undergraduate and graduate students. Is that
mandatory co-op?
Undergraduate is based on a required co-op-based system. Basically, we have a 5-year system. So first year and the 5th year are other schools, freshman and the senior. Then middle 3 years, students take one academic semester in school, then next semester they go to co-op, then they come back, they alternate. So all our students, they have 5 semesters of co-op when they graduate.
That's mandatory too.
Okay. Let's see. Mark has got some comments here. Mark Fry, come in, Mark.
Good morning, and thanks for a great presentation. I just wondered what you saw. I'm from ANSYS Granta. I just wondered what you see as the main obstacles to expanding out this to the aerochem, civil and bio programs, and how do you plan to overcome those obstacles?
Can you repeat the question? I'm sorry.
Yeah, I think he's asking what are the obstacles to expanding this to aero and chemical. I think it's a question of impressing, having a discussion with the faculty and impressing on how this would benefit the students and make their job easier to actually basically impart the concepts to the students because it reinforces it. And of course, the support is required. Jay, you want to chime in?
Yeah, actually, we expanded a little bit to aerospace, one course that is to explore how it goes. And then, of course, aerospace is a special case because almost 90% of their applications coincide with MEs. So it's a matter of just it's a time and our resources. So because in mechanical engineering, we did this first for mechanical engineering program, but we plan to expand to aerospace. Then chemical is their main use is going to be CFD. Then the problem with the civil engineering is that they have a slightly different software landscape there, like Autodesk, those kind of things. So I need a little more, thoughts. What should be the way?
I think, Jay, I think his question is, what are the obstacles to actually moving it there? What do you see as the obstacles?
Oh, I'm sorry. Yes. Yeah. It is. I actually use this because currently I'm serving as department head, so I am talking to fellow department head. Also, I kind of get some help from dean of our college. So dean of our college is highly supportive of buying this concept. He considers this is what we really have to do. So I think kind of it's a top-down approach. Then to make it a little easier, then probably you have to contact individual faculty level as well, because the faculty don't like something that is coming only from the top. Okay, so you need some effort to convert or to get the friends in your side.
Yeah, I think incentive for the faculty in the form of TAs help or other kind of incentives helps a little bit here. I think it's a combination of top-down and bottom-up approach.
Good. One more question, and we'll move to Hans to make some comments. What do you guys see at UC as a way to collaborate with other universities, whether they're, I think Kim mentioned that, and Sam, you mentioned that, in terms within the United States or around in the different parts of the world. What might be some ways that might happen?
I think they just have to reach out to us, and we can sit down and talk about ways we can connect and collaborate, and what common aspects of what we do they see as commonality to them. Then it's easier to replicate and collaborate here. The whole idea of the curriculum here and what we're doing at Siemens is replicable, and that is the key here. So hopefully if we can replicate and give these modules and at least part of these modules, it'll help them here. So they just have to reach out to us. That's all there is to it. Right, Jay?
Yeah. Then more like a sophisticated collaboration can come later. It's like, for instance, one of design courses, then students from 2-3 universities collaborate over the internet, that kind of thing.
Wow, exciting, really exciting stuff. Thank you, Jay. Thank you, Sam. Thank you, Gil. Thank you, Dora. I'm going to hand this over to Hans Hoyer of IFEES and GUDC to wrap it up. Well, over to you, Hans.
Many thanks, Krishna. This is Hans here. I really want to thank you, Dora, for facilitating this connection, not only with your colleague Gil of Siemens, but also with Sam and Jay in these very, very thoughtful presentations. We value that, and we can look forward to continue facilitating these kinds of very creative webinars. One of the thoughts, just final, for you to be aware of, and the concept of aerospace was mentioned. Both IFEES and GDC have some very close partnerships with both.
What happened to your voice, Hans?
We have a very close.
Okay, I guess I guess that's not moving
Can you?
forward. Thank you very much, everybody, and I appreciate all your exciting comments and discussions, and I hope everybody will be happy and safe and around the world, and look forward to another exciting future webinars coming up in the future. Just to remind you that there is a recording of this being made, and so it will be available to participants very soon. Thank you very much.
Thank you. Thank you.
Everybody.
Thank you, everybody.
Thank you, Sam. Thank you, Jay, and thank you, Dora, and thank you, Gil, and thank you, audience.
Thank you.
Yeah, just